Okay, so just a quick overview of what this video is about. We're going to look at the link reaction and the citric acid cycle, or the tricarboxylic acid cycle, or the Krebs cycle, whichever you prefer to call it. If we just look overall what's going to happen here. So, right, the link reaction, we start off with pyruvate here, and pyruvate is converted to acetyl-CoA. We get some NADH out there, and we make some carbon dioxide. Then what happens is that the acetyl-CoA here is fed into the citric acid cycle. It goes around the citric acid cycle, releasing carbon dioxide and generating NADH, which can then be used to make ATP. Okay, so anyway, let's look at this in step by step in quite a lot of detail, quite a lot of chemistry detail, much more than you need for the specification, but just to understand what's going on there. Okay, so let's have a look at the link reaction. Okay, right, here's the link reaction. You get pyruvate, which comes from glycolysis, and it's going to react with this coenzyme. This is coenzyme A, which is made from pantothenic acid, which is a B vitamin. You can let's have a look at what happens here then. Right, so we have got we form it's called a thioester. This here is a thioester. It's like an ester. It's got a sulfur in there between part of the pyruvate molecule and the sulfur in coenzyme A. Right, let's see why we lose the carbon dioxide here. So if you have a think about this, we're going to lose carbon dioxide from this carboxylic acid group up here. Right, that pair of electrons is going to go onto there, and that is going to make CO2. So that means you have got 2 electrons there, right? And what they do is they form a bond to that sulfur, and that's how we form acetyl-CoA. And of course, so what's going to happen there is this sulfur was forming a bond to this hydrogen here, so there's a pair of electrons there. So that hydrogen comes off here as H+, and those 2 electrons. So you can see that the pyruvate, in forming acetyl-CoA in this reaction, it is lost 2 electrons. Losing electrons is an oxidation reaction. We need an oxidizing agent for that, and the oxidizing agent is NAD, which is there. Okay, so there's our NAD. That picks up those 2 electrons and a proton, and it becomes the reduced form of that coenzyme, NADH. That can then go on to drive electron transfer in oxidative phosphorylation. We'll talk about that later. But NADH can be used to make ATP. So now we've in that link reaction, we've made a carbon dioxide molecule, we've made an NADH molecule, and we have got acetyl-CoA, which is going to now feed into the citric acid cycle. Okay, so let's move that up a little bit here. Now, what we have got here is we've got this chemical here, oxaloacetate, and we have got acetyl-CoA, which is here. Now, acetyl-CoA, what it tends to do, it withdraws electrons. So you see this hydrogen here, that will come off as H+, effectively, which leaves a negative charge on this carbon here. Right, it's a very good nucleophile, and then you get nucleophilic attack of that onto this carbon here. This carbon, of course, is going to be a partial positive charge on it because it's connected to the oxygen. So it's nucleophilic addition. That's what's happening there, really. Okay, so if you do that, you can now see that the that those red carbons have been transferred onto the oxaloacetate, and it's now making citric acid. You can see those two carbons there, drawn them in red. The green oxygen, well, that comes from, you can see here, the coenzyme A has got to be split off from the acetyl-CoA. So the water, got this green water here, the pair of electrons will move onto that carbon, and then you regenerate so that pair of electrons will end up going to the sulfur there, and you'll end up with regenerated coenzyme A there. So we're just trying to think about where all the electrons go to and all the atoms go to. Right, so we've got citric acid now, or citrate, because it's the pH of the cell. It will be like that, and now that's going to get dehydrated. Okay, it will get dehydrated, so we're going to lose that OH and one of those hydrogens, and we're going to form a new double bond there, and that is called aconitate. Okay, and it's cis-aconitate because you've got a double bond there. Right, now what's going to happen? So there's not much energy involved in that. So it's just a dehydration. Then you're going to rehydrate it with this water molecule. So we're going to get an OH is going to stick on that carbon there this time, and the H is going to stick on that carbon. So it forms like an isomer of citric acid called isocitrate. So we'll have a look at that. So here we've got isocitrate. All we've done, look, is we stuck the OH and the H there. Now I've drawn that. I've kind of changed the position of those around there. I've just moved. Can you see these red ones? I've just swiveled them around so they're on the top, and we're looking at this carboxylic acid like it's coming off the main chain. Now we're going to lose that carboxylic acid in this next step. So let's have a look what happens there. Right. It's very similar to the decarboxylation, so losing CO2 from pyruvate. So we've got a pair. Right, those electrons there, they are going to go onto there and form a double bond. So that means we've got a pair of electrons there, which are not needed by the CO2. So we get CO2 given off there. And they just pick up a proton in the next. So if you look at this, that will pick up an H+, so that will become a CH2 in the next step. So you have a look here, right? You can see there it's become a CH2. Now this step is a reduction, and we'll see why this is a reduction, because it's an oxidation. We're going to lose electrons. If you look here, we have got an OH group, whereas in the alpha ketoglutarate, which is this molecule here, that OH has now become a ketone. We know that's an oxidation. Let's just think about what's going on there. Well, you'll have a pair of electrons there. Okay, that you can think of as going to form the double bond. This one will come off as an H+. So that means that hydrogen, that's got two electrons. Okay, those two electrons are used to reduce the NAD+ to NADH. So we've got another molecule of NADH which can feed into the mitochondrial electron transfer chain, and we've lost one of those carbons as CO2. We've got another one to lose, another carbon to lose in this citric acid cycle. Right, so let's go from let's have a look at alpha ketoglutarate then, and we can see here. Right, so we've got alpha ketoglutarate. Well, we're going to lose a minute. GDP is in the wrong place. Get rid of that. Right, we're going to lose this as CO2. Okay, so let's see what will happen there. Once again, it's a very similar reaction to the reaction. It involves coenzyme A. It's a very similar reaction to the link reaction, and the enzyme that does it is very similar as well. So we're going to have a pair of electrons there, right? But this oxygen, those electrons go there to form the double bond, and that forms CO2. So those two electrons there are not needed for making the CO2 molecule. Those two electrons are passed on to the NAD here, and it will reduce the NAD to NADH. If we look at the coenzyme A, well, you can think of that as coming off as an H+, and the two electrons which are in the SH bond, they're the ones which are used to form this bond to the carbon there. Right, so we know we've got this compound here which is called succinyl-CoA, and this is where you get a bonus molecule of ATP. It's not actually ATP, it's GTP. So you get GDP plus inorganic phosphate is going to GTP there. Now all that happens in this reaction is succinyl-CoA goes to succinate. You're going to hydrolyze off the CoA bit, CoAS there, and so you need water for that. So drawing a yellow water molecule there. One of the H's ends up on the coenzyme, and the OH from the water ends up on the succinic acid, or the succinate. I should really put that as an O- there, and an H+, because it would be deprotonated at the pH of and the normal pH in the cell. Now the next step is for succinate to be oxidized, sorry. Okay, it gets oxidized to fumarate. Let's see how that works. Okay, so we're going to keep that H, we're going to keep that H. We're going to form a double bond between there. Okay, so you can think of that pair of electrons there will form the double bond. So this one will come off as H+. But this one here, that hydrogen and its electrons, those electrons, they've got to go somewhere. Where do they go? They go not to NAD this time. It's not a strong enough reducing agent to reduce NAD. You can only reduce this one, FAD, but that can still feed into the mitochondrial electron transfer chain. Right, so now we've got fumarate. It's got a double bond, and that is going to be, so that blue water molecule there, that's going to be hydrated. So you're going to stick an H on that one and an OH on this one. If you do that, you can see you're going to end up with this, which is malate. Okay, now malate, we're nearly there now. We've nearly got back to the start, the oxaloacetate. If you look at the only difference here is you're changing an alcohol group into a ketone group. We know that's an oxidation. Let's just see where the electrons go. Well, we can think of that pair of electrons in the bond there. That can go to form the pi bond in the ketone. So that means we've got hydrogen. That hydrogen comes off, and there's two electrons there. Okay, so you get an H+ and two electrons. Those two electrons go to reduce the NAD+ to NADH. So you get your final molecule of NADH, and we're back to the start. Okay, so let's have a think about what happens overall then. So that's the whole thing. I just click down here. Right, overall, we are getting acetyl-CoA. You get the free cofactor released, and it's got a hydrogen stuck to the sulfur now. Got to remember that. And we've got both of those carbon atoms have been oxidized all the way to CO2. Now you can see there, remember in oxidation, adding oxygen or removing H. Well, what have we done? We've actually, if you look at count up the oxygens there, we've got one oxygen on this side, we've got 4 there, so we've added 3 oxygens. And on this side we have got we've got 3 hydrogens. On this side, we've only got 1, so we've lost 2 hydrogens. Okay, so that's quite a lot of oxidation going on there. Now, if you oxidize something, you need oxidizing agents, and these are the oxidizing agents. And of course, the oxidizing agents are NAD plus and FAD, flavin adenine dinucleotide. They get reduced to NADH and to FADH2. Okay, so we can see overall, acetyl-CoA is oxidized by NAD plus and FAD to CO2. So we've now generated the CO2 that comes in respiration. Okay, and the next step is called oxidative phosphorylation, and it's for these reducing agents to push electrons through the mitochondrial electron transfer chain, eventually ending up with oxygen, and they'll turn the oxygen into water.